is a minimum or a maximum. Okay. So how do we do it? Well, more bad news. We can't use the second derivative test. And the reason for that is that we care actually only about these specific directions that are tangent to the level of G. And we don't really, we don't want to bother to try to define directional second derivatives, not to mention that actually it wouldn't work. There is a criterion, but it's much more complicated than that. So basically the answer for us is we don't have a second derivative test in this situation. So what are we left with? Well, we're just left with comparing values. Say that in this problem you found a point where f equals 3, a point where f equals 9, a point where f equals 15. Well, then probably the minimum is the point where f equals 3, and the maximum is 15. Actually, in this case, well, we found minima. These 2 points are tied for minimum. What about the maximum? What's the maximum of f on the hyperbola? Well, it's infinity, because the point can go as far as you want from the origin. So, but the general idea is if we have a good reason to believe that there should be a minimum, and that it's not like at infinity or something weird like that, then the minimum will be a solution of the Lagrange multiplier equations. So we just look for all the solutions, and then we choose the one that gives us the lowest value. Is that good enough? Okay. So let me actually write that down, just. So to find the minimum or the maximum, we compare the values of f at the various solutions. To the Lagrange multiplier equations, to the Lagrange equations. Okay, let's do, well, sorry, I should say also, sometimes you can just conclude, by thinking geometrically. In this case, when it's asking you which point is closest to the origin, you can just see that your answer is the correct one. Okay, let's do an advanced example. Okay, advanced means that, well, this one I didn't actually dare to put on part B of the problem set. So instead I'm going to do it. Okay, so what is this going to be about? We're going to look for a surface minimizing pyramid. Okay, so let's say that we want to build a pyramid with a given triangular base. And a given volume. And so say that, I have maybe in the xy plane, I'm giving you some triangle, and I'm going to try to build a pyramid, so I have to find where to put, of course I can choose where to put the top of a pyramid. I guess this guy will end up being behind now. And the constraint, the goal is to minimize the total surface area. Okay? So first time I taught this class, that was like a few years ago. It was just before they built the data center. And then I used to motivate this problem by saying, well, Frank Gehry has gone crazy, and he's given a triangular plot of land. He wants to put a pyramid. There needs to be the right amount of volume so that you can put all the offices in there. And he wants it to be actually, covered in solid gold. And because that's expensive, the MIT administration wants him to cut the costs a bit. And so you have to minimize the total size so that it doesn't cost too much. We'll see if MIT comes up with a triangular pyramid building. Hopefully not. Could be our next dorm. You never know. Okay, anyway, it's a fine geometry problem. And let's try to think about how we can do this. So the natural way to think about it would be, well, what we have to look for first. What do we have to look for? We have to look for the position of that top point. Well, remember, we know that the volume of a pyramid is 1/3 of area of the base times height. Okay? So, in fact, fixing the volume, knowing that we have fixed the area of the base, means that we're fixing the height of the pyramid. Okay, so the height is completely fixed. What we have to choose just is where do we put that top point? Do we put it smack in the middle of the triangle, or to a side, or even anywhere we want? But its z coordinate is fixed. Okay, let's call h the height. So what we could do is something like this. We say, well, we have 3 points in the base. Let's call them P1 at x1, y1, 0, P2 at x2, y2, 0, P3 at x3, y3, 0. This point P is the unknown point at x, y, h. Well, at least we know the height. And then we want to minimize the sum of the areas of these 3 triangles that are, one here, and one at the back. And areas of triangles we know how to express using length of cross product. So that becomes a function of x and y, and you can try to minimize it, and actually it doesn't quite work. The formulas are just too complicated. You never get there.